welcome back. My name is Alex Voss, and you're attending the second section of television education course. And we're going into radio. And I sure appreciate all the people that have been watching on YouTube. The first part of the course, and if you have any questions, you can refer back to some of the earlier classes, and that will answer some of your questions if they come up now. But we're going to start today with radio and work our way up to television. Now, I have a brief overview. This is what we're going to be covering today in radio, and then we'll go into television. And we're going to talk about Maxwell and how he came up with the idea of electromagnetic radiation, and then the Morse code radio telegraphy, and then we're going to go into Hertz, and then into Tesla, and Marconi, and Fresden, and then we're going to talk about some of the physics behind the way radio works. Now let's take a look at some of our first people in history. Our first one was James Clerk Maxwell. Now, Maxwell was the one that came up with the idea about electromagnetic radiation. He was the one that sort of discovered what it was. Of course, everybody was familiar with it because it's like sunlight. It is, the heat that you can feel. Radio is also part of electromagnetic radiation. And what we did when we were talking about it last time, we agreed that it was a combination of a field, an electric field, and a magnetic field. And these two fields in combination with each other made electromagnetic radiation. So James Clerk Maxwell was the first one to come up with the mathematics behind what that was. And so let's go a little further, because that's sort of a review of what we were talking about. I want to talk about the electromagnetic spectrum. To me, it's very interesting. Now, if we look up here, this is the electromagnetic spectrum. We're all the way over here. These are very high frequencies, gamma rays. And then all the way down here is long wave radio. And then we have AM radio, FM radio and television, mobile phone systems. And then we go on up into the infrared. This is visible light here. And then we're going into ultraviolet, X and gamma rays. And if you look, the very lowest frequencies in visible light's red. The highest ones are magenta. And but we're going to be talking about this area down here. Long wave radio, AM radio, shortwave radio, FM radio, all of this stuff here. Microwaves are up here. And the history of these people that came up with the modern radio transmission and broadcast techniques. Let's look further down. Hughes, what he discovered back in 1878, he was working with telephone, English telephone. And they were in another room, and there were sparks being generated off of a battery system. And they found out that when he was listening on his telephone apparatus, they could hear the sparks on the telephone receiver from another room without any wires interconnected. So that's where he came up with the idea of, well, you could send a signal through space. Now let's take a look further at the spark gap transmitter. Now this thing was the very first kind of radio transmitter, and it worked real good when you only had maybe 1 or 2 stations in the whole world. But the way it worked was very interesting. What we have is batteries. These are some old voltaic cells and a telegraph key. And up here you have an induction coil. And this induction coil, what happens is when we click the key, it causes a current flow through this inductor. But when the inductor builds up this, it builds up a current flow, and there's a magnetic field around it, and it builds up to maximum saturation. When the key is released, then all of a sudden that magnetic field collapses real quick. That makes a very high voltage. And that high voltage makes a spark right here. Electrons that jump across the gap. And they cause an ionization between the gap. And when it gets ionized between the gap, all of a sudden the resistance goes way down, causing an immense flow of a high voltage that charges these Leyden jars, which are actually capacitors, and this tuning coil, and see, we can tap on a tuning coil to adjust the frequency or the actual inductiveness of a coil. Well, what that means is when we have a capacitor and an inductor, we have something called a tuned circuit. And the tuned circuit allows us to send or resonate at a certain frequency. They want to oscillate at the frequency depending on the capacitance and the inductance. So when this voltage is created, it makes a great big tone that happens just for an instant. That high frequency tone is coupled through this inductor to ground and then to an aerial. And you could send signals worldwide because of this system. Problem is, it's wideband. You cover about half of your entire lower RF spectrum with it. And so you could only have maybe 10, maybe 20 transmitters in the world. And so after they got better, they quit using this system. But in the beginning, this worked really well for long distance communication. Now let me talk about how that could happen. Let's say that we wanted to send a signal from the United States to Europe. And here's the Earth right here. Okay, here's the Earth. Here's the U.S. right here. And here's Europe over here. Now the atmosphere has an upper level called the ionosphere. Now, because of the way radio works, low frequency radio particularly, I can then have a transmitter here and I can send a signal up into space and it will hit the ionosphere and reflect back down to Earth, and then it will go back up to the ionosphere and reflect back down. And so this signal will bounce all the way around the Earth. Okay? That allows us to communicate over the whole world at lower RF frequencies. Now, let's say I have a transmitter over here at a higher frequency. If I'm like in the FM range, it's different. That signal goes straight through. And so this transmission is only line of sight. It only covers the Earth for a very small area. And so, but back in those days with these low frequencies, we could send signals over the entire Earth using this method. Okay? And I'm going to talk a little bit more about that later. Here's a crystal radio. Now, we had a way of transmitting, now we have to have a way of receiving. In the early days, they didn't have a lot to work with. As a matter of fact, they made, there was an oat company, oatmeal, and they would send you a can of radio oats, and you could actually make your own crystal set. What you do is you'd have a coil of wire, and then you would have one end tied to ground and one end tied up to a very long antenna. And then we had what was called a detector. That's basically a diode. And what happens with that is the signal comes in and then it's turned into DC right here, which you have to have DC to drive the headphones, but it's alternating DC. And that allows us to make an audio signal that we can hear. So this allows us to tune, this brings a signal in, and this gives us a reference to ground so we could have a current flow. And then the detector converts it to DC, which drives the headphones. Isn't that fascinating? Let's take a look at it in depth. If I have an antenna, and this is a symbol for an antenna, and when I have that antenna out in space, it's absorbing the entire electromagnetic spectrum of signals. But if I were to feed that to a coil and take that to ground, and I could tap here, depending on the resonance of this coil, this is a very rough diagram, and then I can put a diode here, and then I can go to a headphone and take that also to ground. The signal comes in here, this selects a frequency, the diode converts it into audio that can run a headphone. What we're having here, we have a carrier wave. and that carrier wave has a signal imposed on it, and let's say it was something like this. That would sort of, once it's come out of here, it would actually make that, which is an audio wave. Okay, so that's how the crystal receiver works. And you have a symbol, schematic diagram for it up there.